can take it during that time, or you can take it on Friday. It doesn't matter which to me.
Fridays are my free days, so.
Yeah. What a downer. I was going to talk about that anyway. So I'll get a review put together, have it posted on Moodle sometime by the end of the week.
How many exams do we have?
2 in the fall.
My best idea.
Any other questions at all? Things going all right? Geometry going all right?
Yes.
Oh, good.
So that was good, great.
Oh, good. All right. Well, let's continue on our discussion then with rings. So we defined what a ring was last time, got up to what an integral domain is last time. So in particular, one way to think of an integral domain is that you have no non-zero zero divisors. Contrary to what your book says, 0 is a zero divisor. So when we discuss an integral domain, we mean no non-zero zero divisors. Or another way to think of it, it's a structure in which your zero factor property applies. You're used to doing zero factor property and solving equations back in algebra class. So you can think of your integral domains are the ones where that zero factor property applies. So if you have a product that's 0, one of them has to be 0. I'm going to go shut the door. So, tutors all get this.
Can I get little bricks here though?
And one of the reasons why it's called integral domain is you should think about the integers as kind of your prototypical example of an integral domain. So what I mean by that is not only does an integral domain, not only do the integers satisfy that zero factor property, they also don't necessarily have inverses. So that's kind of the prototypical example you want to think of as an integral domain. Your rationals, your reals, your complexes are also integral domains. They also satisfy zero factor property. But in those particular structures, anything but 0 you can divide by. So it's a little bit more special. So if you're thinking about a prototypical example of an integral domain, integers is where you want to start. Okay. Or another idea is polynomials. That would be another example of an integral domain if your coefficients come from an integral domain. So we'll play more around with that as we go along. But I just want to try to get you some thoughts of prototypical examples of things, right? So getting your brain accustomed to a catalog of things. So that was the first one I wanted to mention. If you're thinking of something that's not commutative, your prototypical example should be matrices, because the multiplication doesn't flip-flop necessarily. So just trying to get a catalog in your mind of some prototypical examples of things. So then I just mentioned rationals, reals, and complexes. A commutative ring, well, actually, integral domain. Oh, I didn't mention that to start with. Your integral domains also have to be commutative. I didn't write that down in there when I made the definition the other day. Integral domains are necessarily commutative. And an integral domain in which every element has a multiplicative inverse. Why does this thing decide it doesn't want to erase half the time? Has a multiplicative inverse. Is called a field. So prototypical examples of fields are rationals, because you can divide every rational number except for 0. You can divide by it. real numbers. You can divide by any real number you want besides 0. Complex numbers. Those are kind of your big ones to start with. Smaller examples that you might want to come up with from the finite case. So your rationals, your reals, and your complexes, but also your Z mod P's, where P is prime, is also a good example of a field. And remember that why we have all of our wire. Oh, great. OneNote's not responding. That was weird. Why we have multiplicative inverses in all of our Z mod P's. Remember that if you start with a non-zero element in Z mod P, and remember again, we use that little superscripted star to talk about the non-zero things in a set. For us, it'll be either a group or a ring. With the non-zero things, okay. What is the greatest common divisor of that element with P if it's non-zero? Was it 1? It has to be 1, right? Because the only factors of P are 1 and P. If A is non-zero, that means A is not divisible by P. If it's not divisible by P, then their GCD has to be 1, right? So this implies that your GCD is 1. And how can we always write the GCD? A linear combination, good. I can always write the GCD as a linear combination of the two numbers. Bless you. And now if we reduce everything mod P, or think about dividing everything by P, if you will, and looking at the remainder, that second term in there, the Py, what does it become when you reduce mod P? What does Py become when you reduce mod P? Careful. What's the remainder of Py when you divide it by P?
0.
It's 0, right? So that becomes 0, right? So the P becomes 0, you get 0 times Y, which makes it 0, right? So this implies that your AX is congruent to 1 mod P, which means you have a unit, right? I have a multiplicative inverse. So every non-zero element is a unit. Every non-zero element has a multiplicative inverse in Z mod P. So that makes Z mod P a field. So it's a finite field, and we'll talk more about finite fields later. Probably in chapter 5, I think it is. Maybe 6. I don't remember off the top of my head. But we'll talk a little bit more about finite fields and how we can generate different ones. But all of the Z mod P's are fields, where P is a prime. Now Z mod N is not necessarily a field, because you can create zero divisors in Z mod N. All right. So like I said, I'm just trying to build up a catalog of things. There is one more definition. A non-commutative ring in which every non-zero element has a multiplicative inverse is called a division ring. What's that?
I said if they're not common, they're divided.
So,
Also
division rings are, well, I think, generally speaking, I think they have to be infinite, if I remember correctly. Which is interesting because there's a finite division ring that it actually has to be commutative. But we won't do a heck of a lot with division rings. There is one exercise I'm going to have you play with a division ring in particular, but generally speaking, we won't do a lot with division rings. That comes up later. All right, so let's just come up with some other examples, and then we'll do one more definition, and then we'll start doing some different properties of rings. So let's look at, this is number 29 on page 56. They give you an addition table for a ring, and they give you a partially filled out multiplication table for the same ring. So notice that they don't give you what S times T is, they don't give you what T times S is, and they don't give you what T times T is. And they ask you to fill out the rest of the tables. Basically, they just want you to play around with the distributive property. Okay. So, for example, we don't know what S times T is, right? This is one of the ones we need to figure out. Can you rewrite T as the sum of two elements where we're not using T as one of the two elements? No. S and S works, right? S and S gives you T, right? So replace your T with S plus S. Now we've done tricks like this back in linear. Remember when we were showing that 0 times anything was 0? We wrote 0 as 0 plus 0. It's kind of that same idea, right? We're going to rewrite an element that we don't know something about as a sum of elements that we do know something about, and then distribute. Okay. So what do we get now if I have S times S plus S? How can we rewrite that? Yeah, S times S plus S times S. And then we get T plus T. Good, because we know in the multiplication table that S times S is T. And then T plus T is S. Good. So I know that S times T is S. To go the other way around, I don't necessarily know that this is commutative, right? And I don't know what T times much of anything is. So I could do the same trick on the other side. But we know that for rings, I have to be able to distribute both ways, right? So I still get S times S plus S times S. When we do the distribution, I'm just doing it from the right side. But I end up with the same answer. Is that okay with what we're doing? So far, so good. All right, so now the last product we need to do is T times T. How do you think we want to do that?
Lots of S's.
Lots of S's? How do you want to rewrite it then?
Product of S plus S and S plus S.
Good. And then you just get S times S plus S times S plus S times S plus S times S. Right? Get lots of S's like Evan said. We know that T plus T is S, so we get S plus S, which gives us T at the very end, it looks like. We do all the simplifying. So I filled it out. And again, all we did was use the information we were given and the different properties of rings that we know have to, the different properties of how addition and multiplication have to behave nicely with each other. Questions on that one at all? It's just a matter of playing around with the different properties, the different distributive properties. Let's do another example, and this example I think is going to look familiar to you from linear algebra, if you remember. Really, there's two of them that look the same. I'm going to refer to 22 and 25, and I'll just tell you what the difference is between them here in a second. Still on page 56. We're going to, for 22, they're going to define A plus B as A plus B minus 1 and A times B as A plus B minus AB. Your A and B are integers here. Remember we had the one example in linear where we kind of had the wacky addition and wacky scalar multiplication. This reminds of that a little bit. So rather than doing our standard addition and standard scalar multiplication, this one asks us to prove that, actually, I believe it, no, let's say prove. It says that prove that we still have an integral domain even if we change the addition and multiplication to be strange like this. Okay. If I'm going to prove that it's an integral domain, we need to prove that it satisfies all of the ring axioms, where we had several of those, right? And to prove that it satisfies all the ring axioms, and prove that it also satisfies that zero factor property of integral domains, right? So an additional thing to prove. So remember we had all of those ring axioms. What did we have? We had closure under addition, associativity of addition, commutativity of addition. There has to be a zero element, there has to be additive inverses, multiplication has to be closed, and you have to have left and right, multiplication has to be associative, and you have to have left and right distributivity. Right, there's 8 different axioms. And then we also have to show that it's an integral domain, so we have to show that multiplication is commutative, and that if you have a product that gives you 0, one of the elements has to be 0. So there's actually lots of things to prove in this, so we're not going to do all of them. We're going to hand wave at 2 of them. What I mean about that is if I'm just going to talk about it and make sure that we actually agree that what we have. If we look at A plus B, why is it closed? Well, A and B are integers. If I add A and B together, I still get another integer. Subtract 1, I still have an integer, right? So it's closed under addition. Likewise, it's closed under multiplication. We agree? If we do the operations on 2 integers, we'll get another integer back again. Okay. What about commutativity? Well, we'll do commutativity just by looking at it rather than writing it down. If I do A plus B, I have this. What do you get if I do B plus A? I get B plus A minus 1, but the only thing I flipped around was this ordinary addition, right? Didn't change anything. How about commutativity for multiplication? Might as well do it while we're here. If I do B times A, what do I get on the right-hand side? Yeah, b plus a minus ba, but again, all those are the ordinary operations. I get the exact same thing back again, right? So additions commutative, multiplications commutative, right? Let's talk about it. All right, associativity. Let's do one of them, but not go through a big long. Let's do addition and not the multiplication, because it's just a matter of pushing the symbols around. If you want to show that a plus b plus c is the same thing as a plus b, and then plus a c. Well, b plus c will be b plus c minus 1, right? And I should say b circle plus c will be b plus c minus 1, right? We agree? What will a circle plus b plus c minus 1 be?
A plus B plus C minus 2.
Good. Yeah, it'll be a plus b plus c minus 1 minus another 1 on the end, right? Because this is what's going in for the b. So we'll have a plus b plus c minus 2. And if we do the other way, if we do a circle plus b, we get the a plus b minus 1. Add it to c, what do you get?
A plus B minus 1 plus C minus 1.
Good. Yeah, a plus b minus 1 plus c minus 1, which is the same. So we really do get associativity. And you could do the exact same thing for multiplication. Okay. The reason why I said 22 and 25 were together, for 25, it's the exact same operations, except that they replaced the minus with a plus. For 25, they just changed these to pluses and made those rational rather than integers, but it's the same kind of idea. There wouldn't be any things different with a plus than a minus here, would there? We just change that sign to a plus on the 2. Get the exact same thing. So again, you can do the exact same thing for multiplication. I'm not going to go through it because, like I said, it's just a matter of pushing your symbols around like we just did with the addition. Okay. Let's do distributivity real quick. On one side, again, I won't do both sides because it gets old after a while. Actually, we don't need. Actually, that's not true. This one we don't need to do both sides because we already argued that the multiplication was commutative. So the works on the left, it has to work on the right. So same idea, work on one side of the equation, work on the other side of the equation, and see you get the same answer. In the first one, we need to add b and c together. According to that definition, that's b plus c minus 1. What do you get when you multiply? Apparently we get quiet.
D plus C minus 1. Minus A B plus AC minus A.
Yep. So the definition of multiplies here says add the two numbers together and subtract their product, right? So add the two numbers together, subtract the product, we get that. I'll worry about simplifying it in a second. Oh, no. Oops. When we multiply A and B together, we get A plus B minus AB. And then when we multiply A and C together, we get the same thing, just with C instead of a B. What do you get when you add those two things together?
Just that whole thing minus 1.
Good. That whole thing minus 1. So A plus B minus AB plus A plus C minus AC minus 1. Well, let's see if we got everything that we wanted. So we've got an A here, and I've got an A here, a B here, a B here, a C here, C here, minus 1 here, minus 1 here, minus AB is there, minus AC, I see in both places. And then I see an extra plus A when I do that distribution there, right? So we really do get the same thing when we simplify. I didn't say this was an exciting problem. This is just what we need to go do when we verify that the axioms are true. Again, this feels like a linear algebra problem, right? We do the vector space things. It's the same kind of concept. Remember, for vector spaces, we also need to determine what the 0 was, right? What the 0 was for that vector space. Same idea here. I need to figure out what the additive identity is for the ring, right? So remember, for additive identity, you need A plus something gets you back to A again, right? What are we going to need to use? 1? I agree. Because you'll do A plus 1 and then minus 1, right? So the way we would write it, if I denote the ring by R, ordinarily we write the additive identity as 0, because the additive identity, so we think of it as the 0, in this case would equal 1, which looks a little bit weird, right? The additive identity is the integer 1 in this case. So now that verifies the axiom with a 0. We also need additive inverses. I need something added to A to get me back to the additive identity, but we just said the additive identity is 1, right? So given A, what do you need to add to A to get to 1? A plus 2? Or negative A plus 2, right?
Yes.
Yeah. Because I got to cancel out my A. So if we're writing it in the notation, I know it's going to look weird, but our negative A in the ring, I'll write it as a subscript just so that we're not getting confused by the negative. The opposite of A is negative A plus 2 in this ring. That's why I wrote the sub R there, just to denote that we really are doing an inverse. I know, so additive inverse looks a little weird, but it's because we've got that minus 1 on the end, right? So we verified that we've got the additive identity and additive inverses. So those were axioms 4 and 5, I think we listed the other day. Which also coincidentally corresponded to the same numbers we used in linear. Look at the list again from linear. All right. Are we okay with those so far? We're not quite done because the problem asks us to show it's an integral domain. Okay. So to be a domain, and if I say domain, I mean integral domain. Notice again, that's another word we use interchangeably with some other idea. In algebra even, right? So for an integral domain, it has to be commutative. Commutative ring means it talks about what the multiplication is commutative. The addition is always commutative in any ring. So when you say commutative ring, we're specifically saying something about the multiplication being commutative. Okay. Integral domain also has to have an identity. Multiplicative, and when we say a ring has an identity, we mean multiplicative identity. Because again, every ring has to have an additive identity, without a doubt. Okay. We said that it was commutative. If we want a multiplicative identity, let me put in a blank again. I need something to multiply times A to give me A again. Bless you. Remember the operation is this, right? What do you need to plug in for the B just to get A left alone? 0, man. 0 works. I know it's backward, isn't it? The additive identity is 1. The multiplicative identity is 0. A lot of times for rings, if you're talking about the multiplicative identity, you write 1 sub r. So in this case, it's equal to 0. So 0 equals 1 and 1 equals 0. Math past calculus gets weird. It's fun though.
Are you ever past calculus?
Well, as you don't get finished, you're just past it. I say past calculus. I mean past the classes we call calculus, right? Yeah. There's a whole field of mathematics called analysis. That's past calculus.
So they think.
Analysis is hard. It's not an algebraist. There's a lot of things in analysis I don't get. That's okay. I don't have to get it. I'm an algebraist. I don't have to get it. Is it scary when your professor says something's hard?
Oh, yeah, quite a bit. Some would say.
Analysis are, well, I also say counting is hard. Because the more things you have to count, the harder it gets. Anyway, we have a multiplicative identity. Fantastic. All right, so now we need to show that it's an integral domain. So now we need to talk about two numbers multiplying to the additive identity, the 0 of the ring. What really are we saying when we're talking about that equation? Given the operations and what we just talked about, what equation are we really trying to figure out?
Inverse. So we're finding the multiplicative inverse?
If we needed them all, we would have to do. If we were doing inverses, I would set it equal to
I
would do it. Yeah, so I'm looking for zero divisors. Right, that's exactly right. I'm trying to see if there are any zero divisors. Right, that's what I'm asking in this case. Are there zero divisors? We defined A times B as A plus B minus AB. What is the additive identity in this ring? 1. Yeah, 0 equals 1 in this case, right? Sounds really weird. So what can we do? If let's move the 1 over to the other side. Let's do it this way. Set it up that way.
Yeah, would B not be 1 to get 0?
That is one of the options. How does that factor? How would we factor it? Well, what can I factor out of the first two terms? A. And let's factor out a negative A. If I factor out a negative A, what are you left with? Yeah, negative 1 plus B, or better known as B minus 1. And now we factor that, we get B minus 1 times.
Oh, B minus 1 times negative A plus 1.
Yep, or I'll write it as 1 minus A. Yep. Now this is ordinary multiplication in the integers, right? So what can I say about that product being 0? What has to be true? Yeah, B is equal to 1 or A is equal to 1. So B equals 1 or A equals 1. But 1 is better known as the additive identity in this ring, right? So B is actually either the additive identity or A is the additive identity, which is exactly what we would need for it to be an integral domain, right? It has no non-zero zero divisors. The exact same thing would be how you would prove 25, which is why I put 25 with it. It's just that the plus, instead of minus 1 and minus AB, you have plus 1 and plus AB. But the proofs are exactly the same. Okay. I did this particular problem again, not because it was super exciting, but just to give you an idea of what we need to do to show something as a ring, right? And playing around with an alternative definition of things. Ordinarily, when you deal with algebraic structures, you don't necessarily have these weirdness type of ideas with the multiplications. This is just more of an exercise of playing with the axioms and understanding what they mean. Okay. What does it mean to be an additive identity? What does it mean to be an additive inverse? What does it mean to be a multiplicative identity? Okay. All right. Questions on those at all? All right. So let's do a couple more definitions here. If R and S are rings, we define a new ring, R cross S, by, well, if I want an AB plus a CD, I'm going to say operations plus and times. Sorry. I want to make sure I talk about I need the set of things plus 2 operations. So I need to define what the 2 operations are. All right. If I'm going to take 2 ordered pairs and add them together, how would you like to add them together? Yeah. So guess how we're going to do it? Component-wise. Literally how we're going to add them. Okay. Better yet, if you want to multiply them together, what do you think you would like to do? Also component-wise, yeah. I guess technically this is a theorem more than a definition. The definition is how we define the addition and the multiplication. The theorem is that it really is a ring. But it's not too hard to see why it has to be a ring, right? Where are the operations really taking place? Where do the operations take place? Where does this operation take? Where do these 2 operations take place? So if I'm saying that these are ordered pairs from R cross S, where does A come from? R and B comes from S, right? So where are these operations really taking place? In R, in the ring R, right? But we already know that R is a ring, right? So it already satisfies all the axioms, correct? Where do these operations take place? S, and we already know that S is a ring, so it satisfies all those axioms, right? So showing that addition's commutative, showing that multiplication is associative, showing that multiplication distributes over addition, really is just, well, it does it in R, it does it in S, and we haven't done anything funky, right? These operations are taking place in R, we know they behave nicely. These operations are behaving in S, we know they behave nicely. Okay, so there's not a lot to prove as far as that goes. Okay. What would be the additive identity in this ring? Say that again.
0, 0.
There we go. 0, 0. I agree with you. So the additive identity of R cross S would be the additive identity of R, comma, the additive identity of S, right? Be 0, 0. Because I need to know what do I need to add in the first component to get back to where I started. You need to add 0, right? Likewise in the second one. Now again, those zeros, depending on the structure, may not really look like 0. Right? We just saw in the previous example that 0 was 1. Right? Agreed? Okay. But generally speaking, to get the 0 in the Cartesian product or the direct product, I'll say direct more than Cartesian. To get 0 in the direct product, I just do the 0 in each component. Does that make sense? Okay. What would the additive inverse of an element look like?
The same. That's the -1 R, -1 or -A R.
Yeah. No, I'll just leave it as a negative A and a negative B. Exactly. Yeah. Just knowing that we're doing the inverse of A in R and in S because we're in those components. Yeah. If R and S are commutative, then R cross S will also be commutative. Right? Because again, the multiplication is just taking place in the components. Okay. What about the multiplicative identity? What would be required to start with? What would be required in order for R cross S to have a multiplicative identity? What better happen in terms of the component rings? If you want AB times something to give you AB back again, they both better have an multiplicative identity, right? I better have one here and one here. Right? So the multiplicative identity will be exactly that. Use the multiplicative identity in each component, right? So let's do a couple of examples with Cartesian products here. Let's just make one up. Let's look at let's say we do Z3 cross Z2. First off, how many elements would we have? How many elements does Z3 have? How many? 3? Okay. Are you sure? How many elements does Z2 have? 2. Right? So how many elements is Z3 cross Z2 going to have? Why do we use a cross in the middle like that? What does an X make you think? In between two numbers.
Oh, it's 6.
It's 6. You multiply them together. What are the 6 elements? What are they?
That's an awesome question.
Well, what are the elements of Z3?
No, maybe.
What is Z3?
I'm thinking of graphs. Am I wrong for the graph?
A 3-dimensional, or a plane of all real integers with 3 coordinates.
Oh, you're thinking about way too hard.
No.
What is Z mod 3?
Oh my.
Oh.
You were thinking really hard there.
Yeah.
0, 1, 2.
Ah, there we go. 0, 1, 2. What is Z2 then? 0, 1. Okay, so what are the elements going to be? Ah, 0, 0. What? Okay, what else we got? Oh, 0, 1. What else we got? 1, 0. 1, 1. So on and so forth for the last 2. Oh, I'm done. I got 4. I can't possibly do 6.
I didn't want to say anything else. I don't want to risk messing up again.
And so on and so forth. All right, there we go. There are the 6 elements. What's that?
My pride has been
Exactly. You made me both myself.
Shoo. You were looking at lattice points in 3-dimensional space, is what you were telling me.
Yes.
Yeah, that's what you were telling me. That's a lot harder to deal with. I
I
wanted something with 6 elements in it. You wanted something with more than 6 elements in it.
I was trying to figure out how to get back down to 6.
Yeah. Yeah. All right. Are we okay with those elements? All right. What's your 0 element? What is the additive identity?
Please say 0, 0.
Okay, good. What's your multiplicative identity?
1.
1, 1. I agree. All right.
So nice.
Okay. So if we made up, let's do an addition table and a multiplication table. All right. I'm going to put 0, 0 as my first one here. And I'll put 1, 1 as my second one. And then I'll just fill in the rest of them. So 0, 0, 1, 1. And then I'm not really too worried about the order of the other ones. I'll do 0, 1. Probably didn't leave myself enough room here. What else do I need? 1, 0, 2, 1. Goodness gracious. About 2, 0, and 2, 1. Not really too worried about the order of the other ones. I was just putting the other ones. I put the multiplicative identity, the additive identity and the multiplicative identity in kind of the usual spot, if you will. All right. Let's fill in the gap. Let's fill in the table. Well, we already know. You already told me that the additive identity is 0, 0. So I can fill in the first row and the first column here pretty quickly. Now we're doing addition in the first case. What do you get when you take 1, 1 and add it to itself?
2, 2.
2. I agree with the first two.
2-0.
Why is it 0?
Because the second one's mod 2.
Good. The second one's mod 2. Good. I agree with you. Do 1 plus 1 gives you 2 in the first component, and 1 plus 1 gives you 2 in the second component, but we're doing everything mod 3 in the first component and mod 2 in the second one. Okay. What do you get when you do 1, 1 and add it to 0, 1? What do you get?
That's just 1-0.
That's 1, 0. Good. 1, 1 added to 1, 0.
2-1.
2, 1. Good. 1, 1 added to 2, 0. 0, 1. And the last one's going to be
0-0.
good. That okay? We see where we're getting those? No, now's the time to ask. Let's do the next one. What do you get when you do 0, 1 plus 1, 1? You're going to get 1, 0. 0, 1 plus 0, 1 gives me 0, 0. Good. 0, 1 plus 1, 0 gives me, what was it? 1, 1. 0, 1 plus 2, 0 gives me 2, 1. And finally, the last one's going to be 2, 0. We okay with those? How we're getting those? Okay. The next one will be 2, 1. And the next one will be 1, 1. And good. 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 Yep, I agree. And notice I could have saved myself some time. Addition is commutative, right? So I could have taken that second row and wrote it also as a second column, right? And could have taken the third row, wrote it as a third column. You could save yourself some time with some computations. So I already know that the first column will finish out as 0, 1, and 0, 0. This third column will finish out as 2, 1, and 2, 0. And that fourth column will finish out as 0, 0, and 0, 1. Just saving ourselves some time. 2, 0 plus 2, 0 will give me 1, 0. 2, 0 plus 2, 1 will give me 1, 1. And that'll also go down here. Then finally, 2, 1 plus 2, 1 gives me, I'll get 0, 0. 1, 0, yeah. All right, so that filled out the addition table. Let's see if we can finish out the multiplication table. 0, 0 times any of those things is going to be what? 0, 0. Good. So I'll get 0, 0 all the way across the top and all the way down the first column. 1, 1 is also our multiplicative identity. So when we multiply the 1, 1 across everything, we just get that thing back again, right? What do you get when you do the 0, 1 times the thing? 0, 1 times 0, 1 gives you 0, 1. 0, 1 times 1, 0 gives you 0, 0. Good. 0, 1 times 2, 0 gives you 0, 0. 0, 1 times 2, 1 gives you 0, 1. Good. And then again, I can fill out the third column. because the multiplication here is commutative. What about when we do 1, 0? What do we get going across the row?
1, 0,
Okay,
2, 0,
good,
2, 0.
good. And again, we can go down the column like we did with the row. Because again, the multiplication is commutative. All right, what if we do 2, 0 now? How do we fill out the rest of the row? 1, 0 and 1, 0, good. Because 2 times 2 is 4, but 4 mod 3 is 1. And then finally, 2, 1 times 2, 1 gives me 1, 1. Are we okay with filling those out? Okay. Let me ask you a couple of questions. First one, is Z3 cross Z2 an integral domain? So remember, integral domain is commutative ring. That's okay. With identity, that's okay. With no non-zero zero divisors. So I'm asking you, are there non-zero zero divisors here? Are there two things that are not equal to 0 that multiply to 0? Yeah, there's lots of examples, right? Give me one pair that multiplies to 0. 0, 1, and 1, 0 do, right? 0, 1, and 1, 0 multiply together to give you 0, 0, right? So remember, when we say a product equal to 0 and the two factors are not 0, remember we're saying the product is equal to the additive identity. The additive identity here is 0, 0, right? So I'll have two things that multiply to 0, 0, but neither of which are 0, 0, which that works. There's other ones too, right? 2, 0 times 0, 1 works as well. 2, 0 times 0, 1 times 2, 0 works. There's lots of different examples, right? Notice that anything with a 0 in it will be a 0 divisor because it matches up with another pair that has a 0 in the first component. So in particular, a direct product can never be an integral domain, ever, unless you have what's referred to as a trivial ring, a ring with one element in it, which we don't deal much with trivial rings. But a direct product can never be an integral domain, no matter what the component rings are. If I get a good true-false question while I'm mentioning it. Okay. What's that? A direct product can never be an integral domain. I should say a direct product of non-trivial rings. That's an example of a ring. That would be a trivial ring. Trivial because the only thing it has in it is 0. Not very interesting. Or maybe you find it very interesting. It's like, well, that's easy to deal with. Okay. All right. What are the units? What elements have multiplicative inverses in this ring?
Can you repeat what you just said? Sorry.
That's okay. What elements are units? What elements have multiplicative inverses? I'll give you a hint, there's 2. What are you looking for when you're looking for something being a unit? Equals the multiplicative identity, right? So you want an element times another element gives you the multiplicative identity, right? What is the multiplicative identity in this ring? 1, 1. So, looking at the first row, does 0, 0 have a multiplicative identity? Is there anything you can multiply by 0, 0 to give you 1, 1? No. How about the second row? Yes. So 1, 1 multiplied by itself is 1, 1, right? Okay. What about 0, 1? No. What about 1, 0? Nope. What about 2, 0? Nope. What about 2, 1? Yeah, 2, 1 times itself is, right? So your set of units, which we denote U of R, this is the set of units. Again, units are the things that have multiplicative inverses. In this case, we're looking at the units of Z3 cross Z2, and you just told me, oh my heavens, why are you such a pain with erasing? Okay. Oh, now you've got the eraser going. Thanks. Is 1, 1 and 2, 1. Let's go back and look at the component rings again. What are the units in Z3? What elements of Z3 have multiplicative inverses? Okay. Let's look at just the ring itself and not even worry about the fact that it's a 3. Let's talk about ZP, where P is a prime. What did we say that every non-zero element was in ZP earlier today? You can find something multiplied to give you 1, right? Everything in Z mod, every element that's non-zero in Z mod P has a multiplicative inverse. Every non-zero element of Z mod P is a unit, right? Right. So the units of Z3 are what? 1 and 2, right? What are the units of Z2? Just 1, right? There's only one of them, right? So you've got 2 units in Z3 and 1 unit in Z2, and you're trying to put them together, you get 2 total units, right? This is exactly what we got. To get a unit in a direct product, each component has to be a unit. I'll say it again. The units in a direct product come from units in each component. So if I write it this way, that's true in general. I can take the units of the first ring and do the direct product with the units of the second ring. And then I get the units of the direct product. Direct products are fun things to play with when you're looking for zero divisors in particular. Because I just mentioned a little bit ago, direct products can never be integral domains. They're always going to have zero divisors, as long as you aren't dealing with trivial rings, which are not very interesting anyway. Okay. Questions on that at all? All right. Let's do one more definition and play with that a little bit. We're going to let R be a ring and let S be a subset of R. That's not empty. Non-empty subset of R We don't want empty subsets. That's not very interesting. We say that S is a subring of R if. Well, remember when we did linear, we had vector spaces and then we had subspaces, right? When we went from a vector space to a subspace, did we change anything with the operations? Or did we use the exact same operations that we had in the original vector space? The same, right? So it's the same idea with subring, is if S is a ring under the same addition and multiplication, of R. So, quick example. We know the integers form a ring under addition and multiplication, right? The integers form a ring, right? Blot it out. Can you give me an example of a subring of the integers? Something that'll be smaller, but still be closed under the same addition and same multiplication. In some sense, can you think of something that's half as big that'll form a ring under the same addition and same multiplication? I mean, I know it's infinite, so half as big doesn't make a lot of sense, but can you think of something that's half as big that would still satisfy the ring axioms? What do you think we're trying to get at when I'm saying it's half as big? What numbers do you think I'm trying to get you to think of? Fractions would be the rationals, right? So I want to make sure I stay in the integers.
Oh,
Evens, yeah. Are the evens closed under addition? Yeah, they're closed under multiplication. And they're certainly going to satisfy the same ring axioms. And the additive identity is going to be back in there again, right? And inverses will be back in there again, right? So the evens would form a subring. So as an example, the 2z, remember the set of integers we can write as 2 times z? Form a subring. Can you think of another? Why is this being such a pain today? I don't know why one is causing so much issues. Restart. Hang on. No, I don't want to hang on. I want you to reopen. Can you think of another kind of combination of numbers where one's a substring of another? So we just did evens and integers. Can you think of another combination? Of just familiar numbers that you're used to? Was it? Okay, so does the odds work? Because it would need to be still a ring under the same operation. So if I do 2 odds added together, yeah, so the odds won't work, right? So positives is a good thought. Because if you add 2 positives, I get a positive. I multiply 2 positives, I get a positive. The issue is inverses. What is the inverse of a positive going to be? Negative, right? So what we get is actually a sub-monoid in that case. So we do get something that's interesting a little bit there, but it's not quite a subring. What other sets of numbers do you know besides the integers?
Real numbers.
Okay, real numbers. Can you think of something that gives you a subring of real numbers? Rational numbers will work, right? Because the rationals, when you add 2 rationals, you get a rational, right? Additive inverse of a rational is a rational. all that good stuff, right? So the rationals would be a subring of the reals. What other relationships maybe? Do you think of a subring of the rationals? The integers will work. Yeah, the integers will be a subring of the rationals. Good. Do you think of something bigger than the reals, of which the reals are a subring? Complex, yeah, good. Yeah, exactly right. So there are some subring relationships that you already are used to. Typically, you think of them as subsets, right? But those are all those subsets of the numbers that we talk about are also still closed under the operations that we've been talking about. All right. So, as a theorem, I can't remember what theorem number this is. You can check, and then we'll actually have even a shorter check here in a little bit. But when we do subring, this is theorem 3.2. Yeah, subrings are transitive. Yep, sure are. Yep. Yep. So, well, sorry, I started writing the conditions before I wrote it down. When we say that S is a subring of R if 1 S is closed under the operation, under addition, same addition as R. S is closed under multiplication. Three, the additive identity of R is in S, and 4, negative A is in S whenever A is in S. Go ahead.
I was going to say, just semantics wise, you could combine 1 and 2 to just describe it as the same operations of R.
Mm-hmm. Yep, you sure can. Yep. Yeah. Same other operations of R. And also, you can shorten some of this stuff down too. Remember, we shortened our space test last time and linear down to two conditions. Well, we're going to shorten this in the next section as well when we get to that. All right. Let me give you some problems to work on out of this section. Let's see. This is on page 54. What do I want you to actually turn in? So for practice, I want you to do 8 and 19. There's several in here. 35. And then to turn in. So I have several I want you to look at, but I want you to turn in some of them. 9, 13, 21, and 30. Okay. Do that. All right.
Those are on page 54.
Yeah, they start on page 54 and go all the way to 57. Yep. Okay. All right. So work on those. Those will be due on Tuesday. Today is Tuesday, right? Yeah. Those will be due on Tuesday.